Hello and welcome to another video. In today's video, we are going to continue talking about limits, except we are going to shift our focus from an algebraic approach to a graphical approach so that we have a very well-rounded understanding of what a limit is. And so let us start by recalling what the definition of a limit is. And so a limit refers to a value that a function f of x approaches as x approaches some value a, but not necessarily equal to a. And so in terms of the notation, we are going to have the limit as x approaches a of f of x, okay? And so here, we are going to take a look at how to compute a limit using a table of values. So our first example, we want to use a table of values to graph the function x squared minus 4 over x minus 2. And if you recall from the previous video, this was one of the functions that we calculated the limit of. And so let's just take a look here. Letting x be equal to -3, we can plug this into a calculator, right? And we are going to have that y is equal to -1. Then at -2, we are going to have an f of x value of 0. And of course, that makes sense because here we are going to have -2 squared minus 4. So that's going to be 4 minus 4, which is going to give us that 0, right? At -1, we are going to have a value of 1. At 0, we have a value of 2. At 1, we have a value of -3 over -1, which is going to give us 3. And then at 2, this is where we have our issue, right? Which is also what we saw in our previous video. We are going to end up with 0 over 0, which we know is undefined, right? And then at 3, we have a value of 5. And so we're all good again. So clearly the issue here is at 2, right? And so we want to know what is the limit of f of x as x approaches 2. What is going on here at x is equal to 2? And so we can graph the function, right? We can graph it to try and figure out what is going on here. And so we have a few values. So for example, -3, -1, right? So I'm going to say that here we have -3, here we have -2, here we have -1, 1, 2, 3. And then here, -1, -2, -3, -4, -5, -6. Okay, so our first point is there, and then -2, 0, -1, 1, 0, 2, 1, 3. And then that's where we have our unknown, right? So I'm going to skip x is equal to 2, and then I'm going to go to the point 3, 5. And so if I were to connect these points, right, it would look like a line. And of course, mine is a bit crooked, but that's okay. It would look like a line. But I don't really know what's going on here at x is equal to 2. So I'm actually going to leave that blank for now, okay? And I'm going to represent that with an open circle, because I don't really know what's happening there. we have a hole, all right? We have a hole. So we might wonder, what is actually happening at x is equal to 2? And so in order to find that out, we are going to take some values that are really close to 2, okay? And so here again, using a calculator, when x is equal to 1.5, f of x is going to be equal to 3.5 at 1.9. F of x is equal to 3.9 at 1.99. F of x is equal to 3.99. Here again, of course, if we let x be equal to 2, we still have that undefined value that we don't know what it is, right? But then if we go over the 2 to 2.01, then we get 4.01. At 2.1, we get 4.1, and at 2.5, we get 4.5, okay? And so basically what we have done is that we have divided our function into the values approaching 2 from the left, right? And the values approaching 2 from the right. And this is what is known as our one-sided limits, okay? And the way in which we represent this, the notation, left-hand sided limits are represented using a subscript of a negative sign, whereas right-hand sided limits are represented using a subscript, or a superscript, pardon me, of a positive sign, okay? And so this is going to read as the limit of f of x as x approaches 2 from the left with the negative sign. And it's also going to read as the limit of f of x as x approaches 2 from the right, if we have a positive sign instead. Okay, and what are we seeing? What is the limit? What is the value that f of x is approaching as x approaches 2 from the left? Well, it seems like we are getting really, really close to 4, right? And so that's exactly what we are going to have. We have the limit as x approaches 2 from the left of f of x is equal to 4. And we also have the limit as x approaches 2 from the right of f of x is also equal to 4, because as we go the other way around, it seems like we are getting closer and closer to 4 as well. And so since our one-sided limits are the same, we say that the limit itself, the full limit, the limit as x approaches 2 of f of x is equal to 4. And so our function is going to be approaching that value, okay? So the function is approaching 4 as x approaches 2. And so from here, we are able to draw a couple of conclusions, all right? Very important conclusions. And the first one is that a limit, L, exists at x is equal to a if and only if, which we can abbreviate to IFF, the left hand and right hand limit of f of a exist and are equal to L. Otherwise, the limit does not exist. So basically what we have here in limit notation is that the limit of f of x as x approaches a from the left needs to be equal to the limit of f of x as x approaches a from the right, and they both need to be equal to L in order for us to say that the limit of f of x as x approaches a is equal to L. Okay, so if this is true, if both one-sided limits are equal to L, then the limit itself is equal to L, the full limit. And it is also true that if the limit is equal to L, then the one-sided limits are also equal to L. And that's why this is an if and only if statement. It is true both ways. Okay? And so here we need a quick little note that when dealing with rational functions in particular, there are often undefined values of x, okay, and that is going to be either an asymptote or a whole, where we need to examine the limit more carefully, okay? So if we have a continuous function, like we have seen previously, then we can just plug in the limit directly, and we already know what the function is going to look like. However, with rational functions, where we might have restrictions in the domain, right, that result in asymptotes or wholes, that's where we need to really pay attention to the limit. And so let's take a look here at whether we have asymptotes or wholes. What is the difference? Well, an asymptote, if we cannot cancel it out, then we already know it's an asymptote, right? So if we cannot cancel it out, it's an asymptote. If we can cancel it out, then it's a whole. And I'm saying cancel in quotation marks because we're not really canceling it, right? But if we can cancel it out, then it's a whole. Okay, let's take a look at a couple of examples here. Example 2, sketch the graph of f of x is equal to 1 over x and determine whether the limit at x is equal to 0 exists. All right, so here again, we have a rational function. We have a table of values. Let's fill it out. At x is equal to -3, y is going to be equal to -1 over 3. At x is equal to -2, y is equal to -1 over 2. At x is equal to -1, y is equal to -1. At x is equal to 0, we are going to have 1 over 0, which is of course undefined. At x is equal to 1, we have a value of 1, and at x is equal to 2, we have a value of 1/2, and at x is equal to 3, we have a y value of 1 over 3. Okay, and so let's take a look here at what happens when we graph this function, right? And so here we are going to have again our x values of -3, -2, -1, 1, 2, and 3. And then here I'm only going to need -1 and 1 over there. Okay, and so what am I going to have? Well, when x is equal to -1, y is also equal to -1. When x is equal to +1, y is also equal to +1. When x is equal to 2, y is equal to 1/2. So I'm just going to draw it right there. And when x is equal to 3, y is equal to 1/3, which I'm going to draw right there. And similarly, here I'm going to have at -2, -1/2, and at -3, -1/3. So connecting these points as best as we can, this is the overall shape that we get, which should be expected, as we should already be familiar with the parent rational function, right? And so what do we notice here? We notice that we do have a vertical asymptote along the y-axis, right? Or along the line x is equal to 0. And now let's take a look at the behavior of the function as we are approaching 0. Let's take a look at the behavior as we are approaching 0 from the left and as we are approaching 0 from the right. Okay, so here the limit of f of x, or here 1 over x, right? As x approaches 0 from the left, well, what is happening as we are approaching 0 from the left? We are going down, 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 down towards negative infinity, right? So the left-hand side limit is equal to negative infinity. Well, what about the right-hand sided limit? What is the limit of 1 over x as x approaches 0 from the right? Well, from the right, we are going to be going up, 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 up. Remember that we never touch that asymptote, right? So the function is just going to keep going up and up and up towards positive infinity. So our right-hand sided limit is equal to positive infinity. Now, even though we are approaching infinity in both cases, we're not approaching the same infinity, right? From the left-hand side, we are approaching negative infinity, and from the right-hand side, we are approaching positive infinity, so that is not the same, all right? And so since the left-hand sided limit of f of x is not equal to the right-hand sided limit of f of x, the limit itself does not exist. And usually we represent that with a DNE. Does not exist. Okay, so this is an example of a case in which we don't actually have a limit at a point. Let's take a look at another example here. Now we have the function x minus 2 squared minus 1, and we want to find the limit as x approaches 2. And so here we should be able to see that we have a parabola, right? And usually parabolas are continuous. And so let's take a look. Let's take a look at the values that we have. When x is equal to negative 3, if we plug this into the function, we can use a calculator or our mental math. Y is equal to 24. When x is equal to negative 2, y is equal to 15. And we keep going. Negative 1, y is equal to 8. X is equal to 0, y is equal to 3. When x is equal to 1, y is equal to 0. When x is equal to 2, y is equal to negative 1. And when x is equal to 3, y is equal to 0. Okay, so let's graph it. What do we have here? So again, labeling our axes, negative 1, negative 2, negative 3, 1, 2, and 3. And then here we'll have our negative 1 there. There we go. And so when x is equal to negative 3, y is going to be equal to 24. I'm not going to include that in the drawing. Negative 2, 15. Negative 1, 8. That's also going to be outside of the diagram here. But when x is equal to 0, y is equal to 3. We can definitely do that. 1, 2, 3. Okay. When x is equal to 1, y is equal to 0. When x is equal to 2, y is equal to negative 1. And when x is equal to 3, y is equal to 0 again. And so now here, connecting these dots. There we go. We have our parabola. And there we go, that's a bit better. All right, so now we have our parabola. And so what does this tell us? Well, really here we can see that as x approaches 2, right, it seems like the limit is going to be equal to -1. We don't have any issues applying the condition directly, right, plugging in the condition directly. And again, even if we use one-sided limits, as we go from the left, we are approaching -1, and as we go from the right, we are also approaching -1, right? And this is again because we are dealing with a polynomial, right? Which are continuous, they don't have any asymptotes or any holes. And so here again, we can either use the algebraic method where we plug in the value, the condition directly, right? Or we can also use one-sided limits to show that the limit does in fact exist. And so method 1 here would be the algebraic method. Which is going to be equal to letting x be equal to 2, which of course is going to be equal to 0 minus 1, which is equal to -1. And of course, that's going to be our limit. Or method 2, we can use our one-sided limits using the graph, right? And so we're going to have the limit of f of x as x approaches 2 from the left is equal to -1. And we are also going to have the limit of f of x as x approaches 2 from the right is also equal to -1. And now here what we have is that since the limit from the left is equal to the limit from the right, which is equal to -1, then we have that the limit itself is equal to -1. Okay? So this is an example where we don't have any holes or any asymptotes, and so we are able to just take the limit directly. What if we have a piecewise function? Okay, so here example 4, what if we have a function that has different conditions? Well, then this is of course going to be a little bit more complicated, right? And so here we have a piecewise function. It's a function that is composed of different functions, right, up to a certain point. So here we have if x is less than or equal to 1, then f of x is equal to 3. And we can represent that visually so that we have a better idea of the function that we are going to have, right? And so here again, -3, -2, -1, 1, 2, 3. Just putting a scale here on our axes. 2, 3. That's our 0, 1, -1, -2, and -3. Okay, so here again, if x is less than or equal to 1, so starting here and going to the left, and we have that f of x is equal to 3. So that's just going to be a horizontal line, right? However, if x is greater than 1, then f of x is going to be equal to x minus 2 squared minus 1, which is actually the parabola that we were just looking at, right? And so here I'm going to use an open dot to represent that that this condition does not apply for x is equal to 1, because otherwise it wouldn't be a function, right, at all. It wouldn't pass the vertical test, the vertical line test. but we are going to have that parabola there. Okay. And so what do we notice here? We notice that we don't have a continuous function and that we actually have a jump. All right. And so let's take one-sided limits to see what's actually going on here. Starting with the limit from the left, we are going to have the limit as x approaches 1 from the left, right? That is the value that we are interested in, of f of x. And so as we are approaching 1 from the left, the value of f of x is equal to 3, right? We are just following along, we're just following along this horizontal line. And so the value is going to be equal to 3. However, if we take the limit of f of x from the right, then we are going to be following along the parabola, which is going to be taking us towards 0. And so, of course, these limits are not the same, right? And so this tells us that the limit itself does not exist, because the one-sided limits are not the same. And so we have to be extra careful with piecewise functions because they're usually not continuous and we are going to have jumps like we see here. Okay. A final example, let's just take a look at another rational function here because these ones are definitely I wouldn't say the more interesting ones, but we do want to see an example of another rational function that is not just the parent function. And so here we have 1 over x minus 3. And so again, we can also graph it. We can create a table of values, even though we have not been given one, right? And here we are going to have, let's just use the same values that were given to us before. 0, 1, 2, 3, 4, 5, and 6. And I am picking these values so that we do have a fairly good range in our y coordinates. So here we are going to have for x is equal to 0, negative 1 over 3. For x is equal to 1, we are going to have negative 1/2. For 2, we have negative 1. For 3, of course, we are going to end up with 1 over 0, which we know to be undefined. So this is going to be the value that we are interested in. At 4, we have a y value of 1. At 5, we have a y value of 1/2. And at 6, we have a y value of 1 over 3. Okay, so here again, graphing it, we are going to have negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, 1, 2, 3, 4, 5, 6, and negative 1, negative 2, negative 3, 1, 2, 3. So of course, we might already know that we are going to have an asymptote at x is equal to 3, right? And then if we graph our function, we are going to be able to corroborate that. So at 5, we are going to have here 1/2. At 4, we have a value of 1. And at 6, we're going to have a value of 1/3. And then similarly at 1, we have a value of negative 1/2. And at 0, we have a value of negative 1/3. And at 2, we have a value of negative 1. it shouldn't be there. It should be right there. There we go. Okay, so connecting these dots as well. We do see that we do have our asymptote right where we thought we would, right at x is equal to 3. And so here again, let's take one-sided limits, right? What is the limit of f of x as x approaches 3 from the left? So here again, from the left, we are going to be approaching negative infinity, whereas the limit as x approaches 3 from the right is, of course, going to be equal to positive infinity. And so here, once again, and this is always the case with asymptotes, right? Or with most asymptotes, I should say. Since these two limits are not the same, then we have that the limit itself does not exist. All right, so let's summarize all of these conclusions. Some important notes here. The limit of a function may be undefined if x is less than a or x is greater than a is not in the domain. And so what does this mean? For example, if we have a function, right, and let's say it's a piecewise function or even just a function that is only defined after a certain point, right, then the limit at that point is going to be undefined because for example, in this case, the left-hand sided limit here, it doesn't exist. We don't know what's happening as the function is going from the left, right? We only know what's going to happen from the right-hand side. So if x is less than a or x is greater than a is not in the domain, then the function, the limit of the function at that point may be undefined. The limit may also not exist if the left and right limits are not equal, like we saw. The limit of a function may exist even if f of a is undefined, and that's what we saw in the first example, right? Even though the function was not defined at x is equal to 2, the function was approaching the value of 4 from both the left and the right-hand side, and all we had was a hole. So if the discontinuity is just a hole, then the limit still exists. Another conclusion is that the limit of f of x may not exist even if f of a is defined, right? And so this is the case of the piecewise function. We had that f of 1 was defined, f of 1 was equal to 3, but the limit itself did not exist because the one-sided limits were not the same, right? And so here I'm actually going to write out when this is the case. This is going to be here, example 2 and example 5. The second one, or the third one, was example 1. And the fourth one was example 3. Or no, actually example 4. Okay. And this one was also example. No, it wasn't. I'm not going to say it was a piecewise function because it didn't really apply to that one. And the final conclusion is that the limit as x approaches a of f of x can be in fact f of a, which was example 3, right? When we were looking at the parabola doesn't have any discontinuities, it doesn't have any holes or any asymptotes, and so the limit at the point is just the point itself. The limit of f of x at a is just f of a. Okay. So I hope that this video was helpful, and if it was, please give it a like and consider subscribing and turning on notifications so that you don't miss out on any future videos. And if you have any questions, then please leave them in the comments below. Thank you, and I'll see you in the next one. Bye!